This is NASA's Space Launch System. It follows a traditional heavy-lift design, defined by its orange core stage and multi-part structure. Standing in sharp contrast is SpaceX's Starship. It is constructed from polished silver panels, giving it a silhouette that looks more like a mid-century concept than a modern rocket. Their flight profiles are equally different. NASA engineers its boosters to perform their task once before tumbling back into the atmosphere to violently break apart. SpaceX designed its booster to descend through that same atmosphere and land on its feet. Both organizations are responsible for the current era of spaceflight, yet their hardware looks as if it were built for two different realities. These physical differences are the direct result of conflicting funding models, risk tolerances, and ultimate mission goals. The engineering starts with the skin. For the SLS, NASA utilizes advanced aluminum-lithium alloys. NASA selects these materials to optimize for a single high-stakes journey. Because deep space missions involve years of exposure to the vacuum, the hardware must be durable enough to withstand the unknown of the solar system. SpaceX opted instead for industrial-grade stainless steel for its Starship. This choice stems from the belief that space travel should function like commercial aviation. If you don't throw away an airplane after one flight, you can drastically reduce the cost of the trip. This difference is visible during re-entry. NASA uses an ablative heat shield that peelingly burns away to carry heat away from the craft. SpaceX uses static ceramic tiles designed to deflect that heat and remain intact for the next launch. NASA's alloy is optimized for the durability required of a one-way trip into the deep space unknown, while SpaceX's steel is selected to survive the high-frequency cycle of a reusable fleet. Below the skin, the propulsion systems reveal a different approach to risk. On the Saturn V, NASA achieved liftoff using just 5 massive F1 engines. The goal was singular, raw power. For heavy payloads destined for the Moon, NASA prioritized a small number of ultra-powerful engines designed for high-stakes reliability. In contrast, the SpaceX Super Heavy booster utilizes a cluster of 33 smaller Raptor engines. This creates a redundant system. If a few engines fail during ascent, the flight computer throttles up the remaining 31 to compensate, allowing the mission to continue. NASA relies on singular, high-output power for the distance of deep space, whereas SpaceX utilizes a network of engines where individual failure is a manageable variable. These engineering choices are driven by the source of the funding. NASA receives a steady stream of resources from the U.S. government. This allows them to invest in decades of research for non-profitable, ambitious missions, like establishing a permanent presence on the Moon or Mars. However, because they are spending taxpayer money, NASA's process is inherently more political and risk-averse. Every failure must be justified to the public, making the development cycle slow. SpaceX, as a private entity, relies on commercial contracts to keep its facilities running. Without a guaranteed safety net, SpaceX must be scrappy. They prioritize reusability to keep launch costs low enough to remain competitive in a commercial market, leading them to take aggressive risks during testing. Government funding provides the decades of development needed for deep space survival, while a commercial model demands the immediate efficiency of low-cost operations. NASA has explored reusability before. The Space Shuttle was designed so that the orbiter and solid rocket boosters could fly multiple missions, but the execution was difficult. The high cost of refurbishing the craft after each flight, along with the national tragedies of the program, ultimately led NASA back toward traditional, single-use designs for deep space. Today, these two models are beginning to merge. While NASA uses the SLS for the initial launch, they are actively contracting SpaceX's reusable hardware to handle the final landing for upcoming Artemis missions. The future of space exploration likely requires both approaches: NASA's specialized engineering to survive the deep space unknown, and SpaceX's logistical efficiency to build the highway there.